Hello, it's Keith here and this is lesson 40 of the platform-specific series of my 68000 assembly programming tutorials. Now today we're looking at sound on the Genesis once again. We looked at sound before. This is the ChibiSound Pro driver, my little music driver. We looked at it before on the Genesis, but we were using the legacy Sega Master System programmable sound generator. This time we're going to use the FM synthesis of the Genesis, which is going to give us a much wider range of tones, which is going to be far better. Now unfortunately, at least for someone like me with very little musical experience, using the FM synthesis is a little bit tricky, and what we're going to do today is we're going to go through it extremely quickly. I'm going to show you my example, show you the settings I've used, and of course you can download it, and I'm going to briefly discuss how the sound is configured, but I can't give you a full description of how to configure musical instruments and things because I simply don't really understand it in that level of depth. Now we're creating this thing called ChibiSound Pro today. This is a successor to my original ChibiSound simple sound driver. ChibiSound Pro is designed for simple music. It's designed to effectively emulate an AY style sound chip on all of the hardware, and this means we can play music on multiple systems in the same way. Now we are using 3 registers on the 68000 systems to configure the music. The D3 register is the channel number and also the noise on and off. The top bit of the byte in D3 will define whether the noise is on or off. D6 is the volume, and D2 is 16 bits, and that is the pitch. Now these are matching the Z80 versions. This was originally a Z80 music piece of software, and it's a multi-platform piece of software, and the intention of it is that we can compose our music once. We can then compile it to a binary file once, and that binary file will play in roughly the same way on every system and sound something like the same music, so that we can spend less time composing music and more time writing games. That's the plan anyway. So that's what we're going to be looking at today. So let's take a look at the actual sort of hardware and discuss the technicalities of the FM sound chip of this system. Now the first thing that we need to understand is the concept of channels, I guess. Now the FM synthesis sound chip has a total of 6 channels, but these are actually split into 2 different sets. 1 to 3 are in one bank and 4 to 6 are in a second bank. Now the first thing we need to do is switch on 4 to 6 because by default they'll be disabled, and then to use those we actually need to use a different set of memory addresses. The sound chip is controlled by a pair of memory mapped registers. So from the 68000, which is what we'll be doing today, we won't be using the Z80, we would use A04000 as the first one to select the register, and then A04001 would be the data port that we would actually write the data to. Now if that will work fine for the first 3 sound channels, but for the second 3, channels 4 to 6, we actually need to use different addresses. So that is how we would control them. Now there are some common ports that are accessible that are controlling both. It's these ones here. You can see there is no equivalent for the channels 4 to 6 because they are common to all of them. The other thing to bear in mind is we can actually read from these ports as well, and we will get the status because we need to check if the sound chip is ready to receive data. I believe we can actually read from any of those ports and we will get the data just fine, that status bit, so that's good to know. Now when it comes to the channels, you'll notice the register numbers have a slightly odd pattern. For example, hexadecimal 30 is the multiply and detune setting. Now you will see that this goes 30, 31, 32, but then there is no 33, and then we jump straight to 34. Well, why is that? Well, quite simply, 30, 31 and 32 are the setting for channels 1, 2 and 3, operator 1. Now the 34 is still relating to multiply and detune, but this is operator 2, and then we've got an operator 3 and an operator 4. So there are 4 operators for the 3 channels. Well, what on earth does all that mean? Well, the channels are the sounds that are currently playing. So the this FM synthesis chip can play a total of 6 channels, and so that means we could have 6 notes playing at the same time. Very good. Well, what about these operators? Well, the operators are the components that can be combined together to create our note. And the way we do this is we have various algorithms, and these define the layouts, if you will, of these operators to create the final tone. So here is a chart of the various algorithms that we have available to us. Now in today's example we're going to be using algorithm 4, which is basically combining these 2 operators, operators 1 and 2 together, and operators 3 and 4 together, and these two parts are then combined into one stream, and this becomes the final output. Now, the last operator within each chain has a special function, and this is where we would set our volume and things. And so a simple one like this, where they're all parallel, these all end up becoming the output. But a more complex one, where there is a sort of longer chain, this has just a single final operator. Now, we're going to be using this one, and we're going to be using it, and we're basically going to configure half of the operators to be a clear tone and half of them to be a noise effect, so that we can do our distorted effects. So algorithm 4 was the one that I found the best, but as I say, I can't claim to be any expert at this. I'm categorically not. Now, the other thing that is rather a big problem that we have to contend with is the various stages of the tone actually being created. Now, within FM synthesis, we often have the concept of what's known as key on, K on. Now, this is when if you think about a synthesizer keyboard, we press down the key. Now, if you think of a piano, in the piano there's a string and a hammer and a dampener that silences the note. So when we press the key, the note will not just immediately start, it will ramp up, but it will ramp up very quickly, and this is known as the attack phase. So the note will become very loud very quickly, and then it will start to fade for a while, and this is known as the decay. But then if we keep the key held down, it will continue to make some kind of sound for a very long period, and this is the sustain. However, finally, when we release the key, known as key off, this will then stop the sound, because the dampener, which is kind of like a bit of foam, will touch the string within the piano, and that will very quickly silence the tone, but not instantaneously again. And this is known as the release stage. Now, we will need to configure all of these stages as well as our operators to create the tone that we want. Now, in the case of today's example, we want an attack that's extremely fast. We want to reach a constant tone very quickly, and we want to silence extremely quickly. We only want a very basic tone for our purposes today, and that's what we're going to try and create. So there we go. So I know that I've gone over that extremely quickly. The reason I've gone over it extremely quickly is I only understand it to a very basic level. Now, the best thing that you can do if you're looking to play around with this kind of thing is give it a go. Now, you can download my example and you can play with all of these settings and try and find instruments that you like. That's really all I know to suggest to you, because as I say, I've only managed to do just enough to get today's example working. Let's be honest. Okay, well, let's go over to today's example and let's actually hear some examples, because that's what we're here for. So let's turn on our oscilloscope so we can actually see what kind of waves are being generated, and we'll have a look at the two examples. Now, the first one is going to be ChibiSound Pro Test. This is the main one that we're going to be considering today. Now you can hear there, this makes a continuous tone, and then if I use the simulated joystick, you can hear we're able to alter the tone by pressing the up and down. Now, I actually use this program to configure the lookup table. There is a lookup table of the notes within the octave, and I've got a frequency analyzer which shows me what the correct frequency is. So that's how I typically configure that lookup table. On some systems I do it mathematically, but in most I find that easier for my purposes. Now, as well as changing the tone, if I press the fire button, you can hear we now are able to create a distorted tone, and that's to test the noise effect. Now, that's just a very simple test for me to check the driver's working. What this is really designed for is things closer to music. So what I've got here is another example. This is from my up-and-coming Chibi Tracks program, and this is playing the original Chibi Akima's theme. Now, the Chibi Akima's theme was originally written in Arcus Tracker. That's a tracker program I didn't write. It's very, very good, far better than mine is, but it's also designed for the AY sound chip. So I then converted that music to the Chibi Tracker Pro that I've written, and then exported it to the binary file for Chibi Tracks. Now, this was exported for the AY sound chip on the Z80, but the binary file that is played on that system is the exact same binary file that's now been played on the 68000 with the Genesis sound chip, and that's all thanks to the ChibiSound Pro driver, which is basically a hardware abstraction layer. It acts as a common way that the music software can say, I want to set this channel to this frequency, figure it out, and that's what the driver will do, and that's what we're going to be looking at today. So let's take a look at today's example. So here it is. Here is the rather monstrous amount of code that we've got. So let's start then. So the first thing I think we need to discuss is how we're actually dealing with the channels. Now the ChibiSound Pro software requires the driver to be passed a channel number from 0 to 127, and it just has to figure out how to deal with that. Now with Chibi Tracks you're really only ever going to be sent 3 channels, but the software does in theory support an awful lot more. But we're going to make sure we can support whatever we're given. And so we've got a lookup table of 8 entries here, and we're going to look up one of these based on our channel number. And each of these entries has a sequence of bytes. Now these relate to the actual settings of the hardware itself. So the first one is the base port number, so A04000 here. Now that is the base port number for the first 3 channels, but then it's 4002 for the next 3. And the reason for that is, if you remember, the first 3 channels use this port here and the second 3 use this one here, and so that's what we've specified here. After that we've then got a single byte, which is the offset within that channel, within the registers. So we've got 012, 012. Well, why is that? Well, that's because, if you remember, the channels use 3 consecutive bytes within each section. So the multiplier and detune have 3 consecutive bytes, the total level have 3 consecutive bytes, and so on. And so we are recording that offset here, 012, in the second byte here. The third byte looks a lot longer and a lot more complicated. Well, what is this? Well, this is the key on command. When we want to tell the hardware to press a key down and start making a tone, we need to send the correct byte sequence to the individual operator key on off register here, register 28, and that controls all of the channels. Now this will basically take 3 bits in the bottom 3 bits, and that's the channel number. So the bottom 3 bits here you see are 0, so that's channel 1 effectively, and the top 3 bits here are telling it the operators to turn on. So I think that's operator 1 on the far right there, so that's off, and the other 3 are on here, and that's the configuration we're using in all of the cases here. And so that's the tone settings. Now if these top 4 bits were all 0 here, that would effectively turn channel 0 off, but because they're not, it's turning it on. Now that is channel 1, that is channel 2, and that is channel 3. So channel 3 is 10 in the bottom 3 bits. But when it comes to channel 4, you might assume it would be 11, being as channel 3 was 10, but channel 4 is 100, and so and then it goes 101 and 110. And I think the way you need to think about this is that maybe the bottom 2 bits are the channel number, 0, 1 or 2, and the top bit is the bank. And so for the first 3 channels the bank is 0, and for the second 3 the bank is 1. I think that's the more logical way to think of that, but basically this is dealing with it for us. So all we're going to need to do is read in from this lookup to get the correct channel, and we've got a function here, ChibiSound Pro get channel address, and that's exactly what this is going to do. Now we've been passed the channel number in D6 here, and we are then just taking the bottom 3 bits, getting a value 0 to 7 effectively. We're then multiplying that up by 8 because there are 8 bytes in our lookup table. We're then calculating the resulting address within the lookup table into A1. We're then reading the port address into A0, so that will be A04000 or whatever for the channel. We're then loading the offset into D5, so that would be the 0, 1 or 2, and we'll be using that later on to set our channels, and you can see that just here. So when we want to set a register within the FM synthesis registers here, so these kind of registers here, to a value, we can use this set sound reg1 to set a single register. Now the first thing we need to do is we need to check the hardware is not busy, and the way we do that is we read in from one of our ports. Any of the ports I believe will work. So we're reading in a byte here, and we're testing the top bit of that byte, and if that is not 0, then we've got to wait. The sound hardware is still busy, so this is a wait command, and so here we're just waiting until the hardware is ready, and then once the hardware is ready we are transferring the register number in D0 to the correct port, and then once we've transferred the register number we're transferring the data byte to the following port. So we would transfer the register number to A04000 and then the data to A04001, or if we were using the second 3 channels we would use those ports instead. So that is how we can set a single register. Now, as I say though, in a lot of cases, we're going to need to set this relative to our channel number. So maybe we want to set operator 1, but the register number will be 3031 or 32 depending on the channel number. And so what we're doing here with this set sound reg 1 channel is we're adding D5 to D0, and that is offsetting us according to the channel. And we've loaded D5 in from our lookup table, and so this is helping us out and making it easier to work with any of the channels in the same way. So that's how we're going to control our registers. So let's start by looking at our initialization routine. Before we use the hardware, we need to set up some common settings. Now in this case, we're always making the same tone in every case, so we're just going to set up one good combination of settings, and then we're just going to use that. And as I say, we're actually switching different operators on and off to make the tone or to make the noise. So again, in a lot of cases, we're not going to need to set very much for each individual note, so that's going to help us out. Now the first thing we're going to do is we're going to turn off the Z80. Now the FM synthesis sound chip can be controlled by the Z80, but for simplicity we're going to use it from the 68000, and I think this episode's already quite complex enough, so we're going to turn it off. Now we do that by writing a hexadecimal 100, and we write that to these two ports here. Now the first one is a bus request and the second one is a reset, and by writing these two in order, we're effectively resetting and then locking up the Z80, and we're never going to release it. This frees up the sound chip for our purposes. If we didn't do this, the sound chip wouldn't make any sounds for us. Okay, so what are we going to do next? Well, the first thing we're going to do is we're going to run a clearing routine, and we're going to clear all of the registers, and we're just going to repeatedly run sound set reg 1 with the value 0 in D1, and D0 is going to go through all of the registers and just write them all to 0. Now we're going to do that twice. We're going to do that first for the second set of 3 sound channels. Some of those aren't actually used, but I think we can write to them just fine because we are, and it's not crashing. And then we're going to do it for the main ones, and that's just to set everything to 0 so that we've got a nice clean starting point, so that we know that any problems we do have aren't as a result of junk data lying around in there. So we're first clearing all those registers, and then we are turning on 6-channel mode by setting the top bit of register 29 here. That enables the second 3 sound channels, otherwise they wouldn't be enabled. We're then setting the low frequency oscillator. This is used for distortion effects, and we're using that for our noise samples. So we're setting that, that's register 22. These are common to all of the channels, so that's why we're doing them here. But then what we're going to do is we're going to have a bit of a loop. Now what we're going to do is we're going to sequence through all of our sound channels, and we're going to set up all of the defaults. So we're going to load D6 with 0, and we're going to sequence through all of the 6 channels. We're going to use the get sound channel address, which is going to calculate the offset and also the base for each of the channels accordingly. And then we're going to set the various options here, and we're going to set them all accordingly. So here, this is the amplitude mod sensitivity, frequency sensitivity, and stereo output. This is B4, so we're turning this on. Now, basically, we're turning the channel on, in fact, but we're also setting this amplitude and frequency option here. You can try changing that if you want. You might get a different sound. A more important one in some ways here is B0. This has what's known as the algorithm. Now, the algorithm is selecting which one of these layouts we're using, and we're using algorithm 4 here, and that is this format here. So if you change that, you will get a very, very different sound. So that's one that's worth playing with if you want to make a different sound. Now, that has set the common entries for the channel. Now the remaining entries have multiple operators, 1, 2, 3 and 4, and so we're going to sequence through the 4 operators using D7. Now D7 is going to track which operator we're working on. We're going to work on all 4, but after each operator is complete, we're adding 4 to D5, which is the offset within the register. Now the reason we're doing this is if you look at, for example, the multiply and detune operator 30 here, if we add 4 to that, we will be then processing 34, which is the operator 2. And then if we add 4 again, we'll be looking at operator 3. And if we add 4 again, we'll be looking at operator 4. So this is effectively going through each of the operators for each of the channels, because we are looping through all the channels up here. And this is within that loop. So we're going to set the various options. So we're setting the detune and the multiply. Now the multiply relates to the frequency, the pitch, so that's quite important. Total level is the volume. Now we're setting them all to 0, which is actually the loudest. We are setting the rate scaling and the attack rate. Remember, the attack rate is the speed at which the sound starts to sound. We're setting the decay rate very high as well. That is how fast the sound disappears. The sustain rate, that's the level which the sound is constant when the note is held down. And we're setting the sustain level and the release rate here. And we are setting envelope generation here. We're turning it off effectively. And we're repeating through all of our operators. Now the final thing we're doing here, we're just putting in one tweak here to operator 2, and this is for the tone channel. So we're making one slight alteration to the sustain option here, the sustain level, and that's to create a nicer tone. So again, you can try changing these. You could try changing some of the other operators to create a different tone if you don't like the one I'm using. Again, I'm not suggesting this is a very amazing example. It's really the best I could manage, because as I say, I'm not particularly skilled at this kind of thing in any stretch of the imagination. So that's our initialization. Let's start to look at the set routine. Now the set routine will be passed 3 parameters: a volume, a channel number, and also a noise bit, and a pitch. Now the pitches, when we're playing music, we will read them in from a lookup table, Chibi Octave. Now the pitches, with the low number 0 will be a low pitch, and 65535 will be a high pitch, but the range will not match on all of the systems. If we want them to match on all of the systems, we need to read in a note from the lookup table here, and if we want a sharp or a flat, we can create one simply by taking 2 values and adding them together and dividing by 2. That will calculate the equivalent sharp or a flat. Now, when we want to set one of the channels, we will just run this ChibiSound Pro set routine, and we will pass the channel number in D6, and that will be converted to an offset and a memory address by the get channel address routine again. Now what we're doing next is we're checking the volume level, and if the volume is 0, then we actually want to silence this channel. Now how do we do that? Well, we're reading in the key on command here, but then what we're doing is we are clearing the top 4 bits that relate to the operators, effectively telling it to turn the operators off for this channel. And that's what we're doing here. We're just writing that to the key on, which is also the key off, because we've cleared all the operators here, and that will silence the sound. And so that is all we need to do if we're silencing the sound. So how do we set the pitch? Well, the pitch on the FM sound synthesis kind of works in a bank and frequency setting, but it does depend on the multiplier. And so the way I've got it set up, we're actually basically just shifting the bits along, shifting them across by 5 here. The parameter we're being passed is 16 bits, but we are just basically fitting it in within this range here. And so we're setting the top 2 bits of the bank to 1 here, and we are then going to write that into the hardware. Now the hardware requires to write the high byte first and then the low byte second, and so that's what we're doing here. We're setting A4 here, and then we're setting A0, and these are the frequency and octave of the channel, so A4 and A0. Now you'll notice there's only 1 per channel. It's not relating to the operators, so that's what we've set there. Now what we're doing here next is we're loading in the key on command into D7. Now we're going to change that command if we want to make a noise. So how do we do that? Well, the other thing we're going to do is we're going to change the frequency mod sensitivity as well. So we're loading in the clean tone frequency mod into D1 here. We're then testing the top bit of D6, which is our noise bit. Now if this is a 1, we want to set a noise on, otherwise we don't. Now if we don't want noise, we're just going to skip the next section. But if we want to make a noise, then what we're going to do is we're going to basically keep the bottom 3 bits of the key on command, because those are the channel number, but we're going to change the bits that relate to operators 1 and 2 here, and this is to turn the noise on. So this is setting our noise operators. Now once we've done that, all we're going to do is we're going to change D1, and we're going to set the frequency mod sensitivity on, and that's going to distort the tone, and that's going to create a noise effect. Now once we've done that, we're then going to send that value in D1 to the register B4. Now B4 is the frequency mod, amplitude mod, and the stereo option here, so that is going to make our tone there. Now the volume on the Genesis is a little bit of a pain. Now with the ChibiSound Pro driver, a value of 0 is a silent tone and a value of 255 is very loud. On the Genesis this is kind of reversed, but it's actually even worse than that. The most significant bit of the parameter we're passing is actually the least significant bit in the byte that we need to write. That is, the bit 0 of the volume bit that we need to pass to the FM synthesis is actually the one that has the most effect on the volume. If this is set, it will effectively halve the volume. Bit 1 will effectively drop it by a quarter, and bit 2 will drop it by an eighth, and so on. And so what I'm going to do is I'm going to take the top 4 bits of the parameter we've been passed and effectively move them to the least significant and flip them around. So we're effectively converting these bits here to these bits here, and we're then inverting the values in those bits as well. And so a value of 0 is the loudest, a value of 1 I believe is half that, a value of 3 is I believe a quarter of that, I think, maybe even lower. So it gets very, very quiet very quickly, but at least we're roughly converting the volumes here for the Genesis's purposes. Now we're then setting the total level of operators 2 and 4. Why operators 2 and 4? Well, if you remember, I said before, it's only the last operator within the chain that has the real effect on the output, so we don't need to set the other operators in this case. So that is setting the volume. Now at this point we've actually done everything we need to, and so the final thing we're doing is turning the key on. Now we are using the register 28, which is only present on the A04000, so we're setting that here, and then we are moving the key on command in D7 to D1. Remember, we potentially tweaked that up here if we were making a noise, and so that's how I'm doing things. So there we go. So a bit of a pain, but we've got at least a usable example, as I say, not claiming it's anything particularly amazing. Now, if you've liked what you've seen, please like and subscribe, and if you want to support me making this kind of quite complex music software, please consider backing me on Patreon, because, not gonna lie, the only reason I'm writing this music tracking software is because my patrons asked me to, and the original idea of it was that I was going to write multi-platform music software so I could write multi-platform games, but the honest truth is I simply don't have time to do so. So I'm not quite sure why I'm doing it anymore in a way. Anyway, I hope you've enjoyed what you've seen today. Thanks for watching, and goodbye.